Okay, so Markovnikov addition has a limitation. And the limitation is rearrangements often occur, right? Because we're going through a carbocation intermediate, right? So if you have, suppose we were adding water to this, right? Then the carbocation intermediate, can you see that I'm going to get a hydride shift? Hydride shift, and that's going to give a rearrangement, right? So, but there is a way to do this without rearrangements. We're still going to get a Markovnikov addition, but no rearrangements occur. Clutch. All right. So the way we do it is we first of all oxymercurate this thing. Okay, with this beast here. Okay, it looks it's a beast. It's ugly, but then we just get rid of it. Okay, so essentially we are doing the same thing we would have been doing. We can go here to here with sulfuric acid and heat, right? So that's the fastest way, that's the best way to do it, the cleanest and simplest way. However, if you're trying to avoid rearrangements, then you've got this alternative called oxymercuration-demercuration. Okay? So the mercuric cation is let's see, the mercuric is the Lewis acid in this reaction instead of the proton, right? So previously what we were having was the pi bond that was coming and attacking. The pi bond was attacking the right? Remember that? That's what we were doing with the acid, okay? Where it's a pi bond. It's not an equal sign, all right? However, what we're attacking now instead is this, all right? So just get your eyes used to that. You should draw it out. Maybe you should draw this out too, and then get your eyes used to that. So this essentially is what we've got here, okay? Now that ACO is that piece there, and frankly, it might be useful to you for to actually draw all these atoms out a couple times just to demystify it for you in your head. Sorry, I'm having a hard time talking this morning. All right, so when the pi bond, this is what we do in acid catalyzed. The pi bond attacks that. That's what I've got on the previous slide. Now, in this case, it attacks the mercury, right, which I said a second ago. But the mercury has an extra pair of electrons. So this becomes associated with that carbocation. Okay? Now, this is called a mercurinium ion. I can't imagine you'll be asked to name it, but the more often you say it out loud and write it out, the more you're going to like it. It's a mercurinium ion. This is an intermediate. It's resonance stabilized, as you can see. Can you see that? And since it's resonance stabilized, this carbon is going to have a partial positive charge on it. That's important. Now, since it has a partial positive charge on it, it's a great place for the nucleophile to attack. All right? The mercurinium ion reacts with nucleophiles. It can be easily attacked by a nucleophile. There we are. And then we just clip this off with sodium borohydride. And there's not much more to it. The two reaction sequence gives the same product as acid catalyzed hydration, except it does not rearrange. Does not rearrange. All right. So if you do this with acid, this is the example I used, I think, in the first slide. If you use this with acid, then we are going to get both products, okay? And you're going to get contaminated with this rearrangement. If you really want this, you have to use this method here, okay? This is 2 steps, oxymercuration-demercuration. This is the oxymercuration step, and then here's the demercuration step. But you've got to put a 1 and a 2 in front of that because it's 2 things going on. All right, so oxymercuration-demercuration is a great alternative to acid-catalyzed hydration. And that's all I have to say about that. Good luck.